Hi there, everyone. Thank you very much for joining us today for our webinar on EMI troubleshooting and pre-compliance testing. Before we get started, I'd like to let everyone know that this webinar will be recorded and you'll be receiving an email afterwards with a copy of the recording. So if you can go ahead and share it with anyone you think would be interested or rewatch it, that would be great. If you're interested in any of the other webinars we'll be hosting or to download any of the free resources we have available, such as white papers and application notes, please go ahead and visit testforce.com/academy and you'll find everything you need right there. If during the webinar you have any questions, make sure that you ask them in the Q&A section in the right side menu bar, and we'll be sure to get to all of those questions as we get to the end of the presentation. I'd like to pass it over to Dylan Stinson, Technical Marketing Manager at Tektronix, to introduce himself and get us started with learning more about EMI troubleshooting and pre-compliance testing.
Hello everyone, thank you for joining and willing to spend your valuable time with me today, wherever you may be listening from. My name is Dylan Stinson, and I'm a Product Marketing Manager for Tektronix's USB-based real-time spectrum analyzers and RF test and measurement solutions. Today I'll be discussing the latest challenges with getting products to pass electromagnetic compatibility and how real-time spectrum analyzers or mixed-signal RF-capable oscilloscopes can be used to diagnose, troubleshoot, and pre-test products for radiated and conducted emissions. And considering the cost of failing, 50% of products fail their first time through, it's worthwhile for organizations to invest in their own in-house EMC pre-compliance and troubleshooting kit. So today you'll learn the differences in these tools and how to perform these important measurements. And please feel free at any time, if you have any questions of course, to type them into the comment box and I'll get to them at the end of the presentation. If we look at the current test and measurement challenges of today, there's a major shift going on in the industry right now. With the proliferation of 5G, Internet of Things, consumer electronics, and new age industrial, automotive, and medical devices, there are now billions of electronics and electrical devices in the world today, and it's literally raising the ambient noise floor in the radio spectrum around us. RF emissions from non-EMC compliant products causes radio frequency interference on products placed in close proximity with one another. Even more so, as switch mode power supplies grow more prevalent in the world, they're also becoming smaller, more efficient, and using higher and higher frequency switching frequencies. All of which can begin to couple out and begin to interfere with analog circuitry or other surrounding potential critical wireless signals. At the same time, there are increased pressures being placed on development teams to deliver more with less, and so the demand for electrical engineers with multifaceted skills with both time domain and frequency domain expertise is of a huge value to organizations today. And so when it comes to spectrum analysis, it's not just about RF. You also need to check for digital control signaling errors, software integration problems, spurious emissions, and coexistence problems, especially in dense wireless environments such as hospitals. Thus, the need for mixed domain engineering analysis capability, including analog, digital, and RF, and being able to identify, classify, and locate interfering sources quickly is critical. With today's presentation, I'll begin by defining what EMI and EMC testing is, why we have them, and why you should care. Next, I'll describe the idea of pre-compliance and how many organizations today are choosing to invest in their own set of in-house compliance testing solutions to cut down on costly trips to the compliance lab and time spent redesigning products. Then I'll describe with examples how affordable real-time spectrum analyzers and mixed-signal RF-capable oscilloscopes can be worked into product development cycles to diagnose, troubleshoot, and pre-test products for passing FCC, CISPR, IEC, or MIL standard for radiated and conducted emissions. So what is EMI? Well, if you don't know, EMI, or electromagnetic interference, is the disruption of operation of an electronic device when in the vicinity of electromagnetic energy of an external electrical source. So either man-made or naturally occurring. Sometimes called radio frequency interference, EMI can cause devices to not operate correctly or how they were intended to. Sources of EMI are usually man-made, coming from other electrical devices such as switch-mode power supplies, internal circuitry, personal computers, cathode ray tubes for older products, just to name a few. But you can also be naturally occurring, coming from things such as electrical storms, solar radiation, or cosmic noises. And well, what is EMC? EMC is electromagnetic compatibility, and it's the concept of enabling our devices to operate correctly in their intended environments, with or in the presence of other electrical devices or sources of EMI. Likewise, a device is said to be EMC compliant when it does not influence the electromagnetic environment to the extent that the functions of other devices and systems are negatively affected. So, to ensure EMC compliance with regulations, many companies have historically employed the services of a specialized test facility or test house to perform EMC pre-compliance and compliance testing. EMC compliance testing requires methods, equipment, and measurement sites that comply with national or international standards and procedures that are heavily dictated by the particular standard your product needs to comply with, which can be determined from what type of device it is and where you plan to sell it. But if testing is performed by a compliance lab, why should anyone else care about testing EMI or EMC? Well, anyone designing, manufacturing, or importing products with electronics inside needs to care about EMC compliance. EMI and EMC regulations are in place throughout the world to provide improved reliability and safety to users of electrical and electronic equipment. These regulatory bodies, the FCC in the US, IEC in Europe, and others, have set specific limits on the amount of unwanted emissions that can be emitted from a device, as well as how well products are immune to EMI. While there are many safety and reliability reasons, the primary goal of these commercial emission limits is to prevent interference to nearby television and radio receivers. Failing to pass EMC compliance prior to release in a market can result in expensive fines, seizures, or even product recalls. Many companies, especially automotive, aerospace, and other manufacturers of critical safety systems, mandate their own emission limits, even more strict than the standards tests, to be even more certain that their products are going to be electromagnetically compatible with surrounding equipment. There have been plenty of cases in the past where EMI has caused problems, and you wouldn't want to have your product result in embarrassing fines, seizures, or legal battles as a result of not considering it in your design or test routines. One obstacle is the lack of expertise to handle RF testing, leading to some interesting workarounds. I recently had an opportunity to talk to a development team integrating WLAN or Wi-Fi to their automotive infotainment system. They used a pre-certified WLAN module, and the project turned out to be mostly a software project. As the software neared completion, instead of performing true EMI and standards testing, their testing involved looking at Wi-Fi speeds as an engineer moved their device various distances from a store-bought Wi-Fi router. Now, it's possible you could learn something from this, but it's a far cry from true electromagnetic characterization and optimization. Here's a simplified diagram of the typical product development cycle. Due to the lack of knowledge of EMC principles among junior engineers, many teams will often go 90% of the way and then begin to think about compliance testing. This is really incorrect and costly thinking. Compliance testing should be considered early in the development with all the risks identified early, test plan outlined, with periodic diagnostics testing, troubleshooting, and standards testing for intentional radiators, as well as pre-compliance scanning in-house throughout development of the product. Performing some practical and easy-to-perform pre-compliance tests will save time and money by identifying potential failures early before they become expensive redesign issues. While the use of pre-certified RF modules simplifies much of the design, as was the case in the previous slide, it won't remove all requirements for EMI or EMC regulatory compliance testing. Many IoT design teams assume that EMI testing is a mere formality. Unfortunately, this is rarely a safe assumption. EMI test fees and repeated board turns can add up quickly, as you can imagine. And as I mentioned earlier, 50% of products fail EMC compliance their first time through. And given that EMI compliance test fees can range from $5,000 to $50,000 per product, it's not unreasonable to suggest that pre-compliance testing would be a worthwhile endeavor for organizations to invest in. Fortunately, Tektronix offers an assortment of tools to help you prepare for these important tests. Before we begin to troubleshoot EMI, we first must have an understanding of where EMI, or sometimes called RFI, comes from and how it's generated. Some of the most common sources of EMI include clock oscillators, switch mode power supplies, I/O ports, cables, connectors, interconnects, and LEDs even, to name just a few. Switch mode power supplies are quite common sources, and it's natural given that their switching frequencies have been increasing over the years to improve efficiencies. The switching MOSFETs and high current loops in these circuits result in fast changes in currents, inducing magnetic fields, and fast changes in voltages, inducing electric fields. Now there are three parts to every EMI source. You have energy, you have to have some sort of energy source, you have a coupling path or a way for that source of energy to transfer its energy out, and you need an antenna. Any wire, metal enclosure, or PCB trace can potentially act as an antenna and radiate that energy into the environment. You take away any of these three and you no longer have EMI problems. Fortunately, you do not need to duplicate test house conditions to troubleshoot EMI test failures. Instead of requiring measurements normally performed in an expensive, highly controlled EMI test facility, you can pretty easily perform your own early troubleshooting and diagnostics yourself on your own time and schedule. While there are many different scenarios depending on the EMI standard you're testing for, here's a do-it-yourself 5-step process for performing EMI troubleshooting and pre-compliance pass-fail testing of radiated and conducted emissions, much of which can be performed using a powerful yet affordable real-time spectrum analyzer or mixed domain or mixed signal oscilloscope. First, early in the development, we use near-field probes to identify and locate sources of high energy and harmonics around our boards and products. Second, we run RF current probes up and down I/O cables and power cables to identify harmonics along cables whose sources can then be traced back to either the unit under test or surrounding environment. Third, taking what we've measured, we must use periodicity and coincidence to zero in on sources and perform calculations to estimate far-field electromagnetic emissions. The fourth step in this is to make incremental fixes, and we do this by following the process of elimination to reduce emissions. We remove, filter, or shield, or redesign one piece of the circuit at a time as needed. With the fifth and final step being able to simulate your own EMC pass-fail testing using a calibrated antenna for far-field radiated emissions testing, or a LISN, line impedance stabilization network, for conducted emissions, giving you the confidence that you'll pass your first time through the compliance lab.
And unfortunately, due to time constraints, I'll only be covering steps 1 through 3 in today's presentation. Steps 4 through 5 will be covered in a follow-on presentation at a later.
So let's begin with step 1, using near-field probes to identify and locate high-energy sources and harmonics.
So the first thing we need to do is set up our spectrum analyzer or RF-capable oscilloscope to take these sorts of measurements. First, we want to connect our probe. Both either the near-field probe or the current probe can be connected in this way to the RF input of the instrument. Then we set the frequency range, start, stop, center, and span. Third, we want to set the resolution bandwidth. It's either 100 or 120 kilohertz usually for EMI testing, below a gigahertz. And we also want to make sure that the video bandwidth is set to auto, set the vertical scale from dBm to dB microvolts per meter, which is most often used for EMI testing. And we also need to set the reference level for the display we're using. I'll typically use anywhere from 60 to 85 dB microvolts per meter for a reference level. And we also want to make sure that any internal or external preamp is turned on, which will give us about a 20 dB boost to low-level signals. So all this can be done using modern spectrum analyzers, which I'll talk more about later, and Tektronix's mixed signal oscilloscopes, which also have frequency domain capabilities.
While fully certified compliance testing procedures are designed to produce absolute, calibrated measurements, troubleshooting can be performed in large part using relative measurements. Near-field probes are essentially antennas, which are designed to pick up the magnetic field or electric field variations. In general, near-field probes do not come with calibration data, so they are intended to make relative measurements to identify sources of EMI. When searching for sources of EMI with near-field probes, it's important to understand how the probes fundamentally work, all of which can be described if you remember Maxwell's equations and the trusty right-hand rule. H-field probes have a distinctive loop design and should be held with the plane of the loop in line with the current flow, such that the loop intersects the magnetic field lines of flux. The size of the loop determines the sensitivity as well as the area of measurement, so care must be taken when using these types of probes to isolate a source of energy. Near-field probe kits will often include a number of different sizes so that you can use a progressively smaller loop to size in order to narrow in on the area of measurement. E-field probes function as small monopole antennas and respond to the electric field or voltage changes. When using these types of probes, it's important to keep the probe perpendicular to the plane of measurement. In practice, E-field probes are ideally suited for zeroing in on a very small area, identifying sources with relatively high voltages as well as sources with no terminations. At low frequencies, the circuit node impedances in a system can vary greatly. Therefore, knowledge of the circuit or experimentation is required to determine whether an H-field or an E-field probe will provide the most sensitivity. At higher frequencies, these differences are dramatic. In all cases, making repetitive relative measurements is important so that you can be confident that the near-field emission result from any change implemented to our board is accurately represented. The most important consideration is to be consistent in the placement and orientation of the near-field probes for each experimental change. Now, a lot of people say, I want to make a calibrated measurement with an E-field or H-field probe. In general, near-field probes are not really calibrated. From a diagnostics perspective, though, that is not much of a problem. From a diagnostics perspective, what we are really looking for is how much change or relative change do we make to our signal. If we have a spot frequency that we know is a problem, and we have tried to mitigate that in some way with some shielding or a change in design, we can measure before and afterwards to find out how much we have affected the change. Also, you don't necessarily have to actually buy probes. Near-field probes are fairly easy to make yourself, and there are many instructions that can be found online. What I will say, though, is please be careful when you are putting together your own probe. Remember that if it has a conductive surface and you are sniffing very close to the device under test or the PCB, you don't want to cause yourself any issues by shorting out the PCB during your test. Most, if not all, vendors' near-field probes are built with a protective non-conductive outer layer, which greatly reduces the chances of a short-circuiting your PCB. When it comes to debugging EMI issues, there are a few targets that I really like to go and look at first. The first place I gravitate to are power supplies, and specifically switch mode power supplies or circuits that involve some sort of switch mode. Switch mode operation can lead to ringing or noise. Depending on the amplitude of the ring, it is a prime place for us to have a source of RF energy. And from an EMI perspective, when we are talking about a specific design, we usually break it down into sources and antennas. Where is the source of the energy, and how does that energy actually leave the board? Second, to switch mode power supplies and switching circuits, I often look at clock and data lines. Depending on the design, you may or not be employing some form of spread spectrum clocking. It is important for us to know how well our spread spectrum clocking is working. After that is looking at a broad term I call resonances. Resonances could be actually in the board itself, could be into wiring diagrams, and could be in cabling, shielding, and harnessing issues. In general, when I first look at a product, I will go to the power supply. The second place I'll go to is what I call the ins and outs of the product, or the I/O ports, which signals are coming into the device and which signals are coming out of the device. Do we have USB? Do we have Ethernet? Do we have RS-232? These are all the sort of things you want to look for. Here's a typical measurement you might see when performing these near-field measurements. Here I'm measuring from 10 MHz to 500 MHz, and I've set my reference level to 70 dB microvolts per meter, or roughly minus 40 dBm when using units of dBm. I can already clearly see some spurious emissions present as well as what looks like some harmonics. I've placed markers on 3 of the largest peaks that I'm interested in, and the marker table tabulates all the details of each of the markers. I'll take a few measurements like these at different locations around my board. Each time I'm saving an image, I also need to note where on my board the measurement is being made at the time. In this case, I was measuring just above the FPGA and clock oscillator, which should account for a lot of the harmonics we're seeing. Most of the time, narrowband harmonics are relatively stable in amplitude. However, there are times when the amplitude can change due to gated digital signals or different operating modes. If the harmonic peaks upward at the wrong time, it could potentially lead to a compliance failure. Swept analyzers, or traditional swept analyzers, can easily miss these infrequent amplitude peaks. Real-time analyzers, on the other hand, are needed for capturing these fast time-varying signals. They essentially allow you to see what other traditional analyzers miss. Here's an example where narrowband, low-frequency emissions of an onboard DC-to-DC converter are coupling onto a small mobile device. The swept display on the left is having a hard time capturing the peak emissions, whereas the real-time DPX display on the right easily captures the peaks and even detects an occasional 6 dB pulsing increase in amplitude. This transient pulsing harmonics could easily cause a compliance failure should it couple out through conduction or radiation. Another thing that can be done is to look at spurious oscillations over time. Here we have both persistence or DPX display on the right and a spectrogram or waterfall display on the left. The bimodal oscillations in frequency can easily be seen in the spectrogram display. You can also get pretty creative with near-field scanning these days. Tektronix, an Italian company working on innovative power electronics, faced challenges in modeling the behavior of EMI emissions of their design layout in order to optimize it. This required a lot of modeling and retest, and the testing time was rapidly growing increasingly costly for the project. They found a solution combining the Tektronix EMC 3D scanner with the Tektronix RSA306B real-time spectrum analyzer, and they needed to run repetitive measurements by scanning with a spatial resolution of 1 millimeter. And running these tests on a relatively large board is time-consuming, depending on the span and resolution frequency used. Prior to using the RSA306B, every single test risked lasting too long with a common spectrum analyzer. For every point on the board of the analysis, the acquisition needed to be completed on a whole spectrum and transferred to a laptop for processing the acquired data. The best companion spectrum analyzer to avoid long acquisition time is the RSA306B spectrum analyzer. This instrument is extremely flexible, small, and reasonable in cost, but the real advantage is its real-time acquisition speed, even at narrow RPWs, which allow it to collect data quickly so that the full scan can be taken in a reasonable amount of time and repeated whenever necessary to immediately see the effects of design corrections. As part of EMI debug troubleshooting, it's relevant to mention our new 4 Series MSO, given the number of innovations it brings to bear for mixed domain debug and troubleshooting. As our latest of our MSO portfolio, the new 4 Series MSO offers the unique ability to flex between analog and digital on the same scope input, which we call flex channel. On a 6-channel scope, you can select up to 6 analog or 48 digital channels or a mix between. You'll also have an award-winning capacitive touchscreen, offering the largest HD screen for this type of scope in the market. And underneath the interface, you'll have hardware that delivers 12-bit vertical resolution, 6.25 gigasamples per second, 31.25 meg record length across all channels. The 4 Series offers 5 high-performance instruments in one portable package, offering fast insights and reliable measurements. Integrated in the scope is a digital voltmeter, arbitrary function generator, frequency counter, and the ability to independently measure in the frequency domain. Though a unique capability, which I'll speak to a little bit more in this presentation, is called SpectrumVu. And the introduction of SpectrumVu, the next innovation in scope functionality, which powered by our proprietary Tech49 ASIC design, uniquely enables simultaneously display time and frequency domain views of the same signal with independent control and acquisition settings in each domain. This is super useful when working with spread spectrum clocks or troubleshooting EMI transients, given the unique synchronized capture of time and frequency domains to debug the most challenging embedded design problems. Now I'd like to just provide you a brief technical overview of how we are able to provide this next generation of time and frequency domain analysis. In the 4 as well as the 5 and 6 series MSO, behind each flex channel input is a 12-bit ADC inside a custom ASIC. As shown above, each ADC sends high-speed digitized data down 2 paths. One path leads to hardware decimators, which determine the rate at which time domain samples are stored. The second path leads to a digital down converter or series of digital down converters also implemented in hardware. This approach enables independent control of the time domain and frequency domain acquisitions, allowing optimization of both waveform and spectrum views of a given signal. It also makes much more efficient use of long but finite record length available in each instrument. As you can see from the block diagram, the channel's signal conditioning is shared, meaning that the analog characteristics, both bandwidth, attenuation, or gain, are shared between both domains. The A to C is also shared by time division multiplexing between both paths. So what this all means is a new way, a much more powerful way, to debug and troubleshoot versus a traditional scope FFT. In comparison with conventional FFTs and the way they're architected in most other scopes, the frequency domain view lacks flexibility and functionality because traditional FFTs are driven by the same acquisition system as the analog time domain view. With a traditional FFT, changing the center frequency, span, or resolution bandwidth will change the scope's horizontal scale, sample rate, and record length in unanticipated and undesired ways. This will often mean that when the optimal frequency domain view is achieved, the time domain view is no longer usable. When adjustments are made to a horizontal scale, sample rate, or record length to again achieve the desired time domain view, the FFT view is then no longer usable. Unlike a traditional FFT, Spectrum View on the MSO 4, 5, and 6 series oscilloscopes provides the ability to adjust their frequency domain using familiar center frequency, span, and RBW controls. And because these controls do not interact with the time domain scaling, it's possible to optimize both views independently. For EMI applications, it provides automated peak markers as well as an ability to apply windowing to filter out undesirable frequencies or harmonics. The underlying INQ data that's used to create the spectrums shown by Spectrum View can also be used to calculate RF first time waveforms, and which show how various characteristics of the RF waveform vary over the entire acquisition, not just where spectrum time is positioned. In addition, the INQ data can be exported from the scope and reanalyzed in SignalView PC offline for more in-depth vector signal analysis. In all, and I'll talk more about this later when we get into discussing periodicity and coincidence of signals, the MSO series of oscilloscopes and their spectrum view functionality allows for time domain and frequency domain correlation with other signals. This ability to simultaneously display time and frequency domain views of the same signal with independent acquisition settings in each domain is an easier, more repeatable means to EMI debug and more towards efficient system analysis. Now that we've covered step 1 with near-field probes, I'm going to start talking now about using RF current probes to identify harmonic currents along cables and I/O ports. Current harmonic measurements are the amount of power distributed among harmonic multiples of the line frequency. These harmonics can feed back into the line, causing power equipment overheating. Current harmonic measurements are an important indicator of power quality and a requirement in many EMI standards. Total harmonic distortion is the cumulative value of the distortion contained in the harmonics of the fundamental line frequency. We will use THD, or total harmonic distortion, as a figure of merit when trying to compare total harmonic distortion as a percentage of the fundamental or total harmonic distortion as a percentage of the RMS measurement. So the probing configuration with an oscilloscope for power quality and harmonics measurements requires a differential probe across the AC input and a current probe on the AC line to measure the voltage and current into the switch mode power supply. Since we're making measurements on the power line, we will need a high voltage differential probe. In this measurement example, we're using a TMD P0200 high voltage differential probe. The power application supported on MSO 4, 5, and 6 series scopes also supports Harmonic pre-compliance pass-fail testing, which can be configured for EN 61000-3-2 or MIL Standard 1399. Compliance testing is an expensive and time-consuming process, and so a compliance test failure can significantly delay introduction of a new product. So pre-compliance allows early testing to the applicable standard and improves your confidence before you submit your product for full compliance testing. For IEC 61000-3-2 pre-compliance tests, the measurement badge at the right side of the screen shows the amplitude measurements of the fundamental and third harmonic of the line frequency, total harmonic distortion as a percentage of the fundamental and as a percentage of the RMS measurement, and RMS amplitude, frequency, true power, and pass-fail is all indicated in the badge. The harmonics results table at the left of the display shows the measurements on each harmonic, as well as it showing the limit specified for the standard, and it also shows the pass-fail indicator and the margin for that particular standard. The harmonics plot at the top of the display shows the magnitudes of each of the harmonics, and the fundamental is in blue, but also a white line is indicating the limit value for each harmonic, allowing easy visual assessment of test margins. Here's another example of performing harmonic analysis. This time we're using an RSA 306B in combination with EMCVu pre-compliance software, which includes some useful tools for troubleshooting EMI and analyzing harmonics. In this case, we're using a spectrum analyzer to measure and compare against limits for the European standard EN 55011. The Harmonic Markers tool allows you to place markers at user-selectable harmonic factors of a chosen fundamental frequency, which is helpful for determining if certain emissions from a scan are caused by a known fundamental frequency. And for example, you'd be able to use this to check if the main emissions measured are related to one of the oscillators on your board. Okay, now that we've done some near-field measurements, taking what we've learned, we now need to use periodicity and coincidence to zero in on sources and estimate the far-field E and H-field emissions. Now that we've identified hot emission areas on our board and have identified harmonics along cables, now what do we do? This is often a question that many people have when trying to debug EMI problems. They understand how to use near-field probes, but now what? Well, this next step of classifying periodicity and coincidence of each of the emissions of interest helps us to determine, based on the spurious emissions and harmonics that we're seeing, where on our board we need to employ any remediation techniques. This will help us and tell us where our sources are based on the periodicity and coincidence of the signal that's being either radiated or conducted through an antenna. Then, once all of the sources and antennas have been identified, we can use calculations and formulas to estimate the far field emission levels and decide which potential emission failures are worth tackling due to them likely to fail at the compliance lab. Fortunately, as I was explaining a little earlier in the presentation, the innovative SpectrumVu feature in the MSO 4, 5, and 6 series scopes provides the ability to look at periodicity and coincidence by allowing for multi-domain analysis. Unlike a traditional FFT, SpectrumVu on the MSO 4, 5, and 6 provides the ability to adjust frequency domain using familiar center frequency, span, and RBW controls. And because these controls do not interact with the time domain scaling, it's possible to optimize both views independently. Here I'm looking at two different channels, looking at both channels with the frequency domain and time domain. This figure shows the behavior of wave impedance in the near field and far field, and in the transition zone between them. We can see that in the near field region, fields can range from predominantly magnetic to predominantly electric. Near field measurements are used for troubleshooting, since they allow you to pinpoint sources of energy, and they may be performed without the need of a special test site. However, full compliance testing is performed in the far field. And one question we often get is, how do I know if a measurement in the near field will end up showing up in the far field? The short answer is it can be complicated. This is because the strength of the far field signal is dependent not only on the strength of the source, but also the radiating mechanism's antenna factor, as well as any shielding or filtering that may be in place. We have to remember this rule of thumb. A signal in the far field should be able to be seen in the near field, but a signal in the near field may not necessarily radiate out and be seen in the far field. Okay, so now I've taken you through steps 1 through 3 of the EMI Diagnostics and Troubleshooting 5-step process. This included using near-field probes and RF current probes to look for high-energy sources and harmonics, and we also use periodicity and coincidence to zero in on sources so we can estimate far-field E and H field emissions. In a follow-on presentation, I'll be covering steps 4 through 5, but for right now, I welcome any questions you may have.
Thank you for listening to our webinar on EMI troubleshooting and pre-compliance testing. There was a lot of information there from Dylan, and we're just waiting for some questions to come into the Q&A box. If you have a question, feel free to type it into the Q&A section on the right-hand side of your dashboard, and we'll get to answering those. Also, I'm going to post a quick poll up in the dashboard, and it'll be available for about 5 minutes. So while we're waiting for some more questions, feel free to fill in your responses. For those of you who attended, we will be sending out a copy of the recording so that you can watch it again or share it with any of your colleagues. And if you do have any questions that come up at a later point in time, don't hesitate to reach out to us at Testforce. You can reply to my email, or you can contact me easily by emailing support@testforce.com. Thank you very much for your attention and participation today. I hope that you all have a great day, and we look forward to hearing your feedback.